Hey class, this is a quick, just very quick lecture on the force on a magnetic charge as it enters the magnetic field. Here is our equation for that force, but before we really get to the equation, let's talk about what's actually going on. If we have some magnetic field, I'm going to draw it as actually let's draw the magnetic field coming. Let's draw a magnetic field pointing up. This is going to be a pretty rough sketch. And we have some charge, positive Q, positive charge, and it's traveling at a velocity v. Across those field lines, it's going to feel a magnetic force. That magnetic force is going to the magnetic force is going to apply a force to my moving charge, which is going to cause it to change direction. The magnitude of the force is equal to qvb sine theta, but really what that means, Q is the charge, V is the velocity. That's easy, those don't change. V is the magnetic field. But this sine of theta is picking out how much of our velocity, or what component of my velocity is perpendicular to the magnetic field. So theta is the angle between the magnetic field and the velocity vector. So in this case, theta is 90 degrees. Theta is this angle here. Here, since my magnetic field is up, this is my angle theta here. Since my magnetic field is up, theta is 0 here. And this also tells us, based on what a sine curve looks like, if this is sine of theta and theta, that if we are in the same direction as of the magnetic field, that is, if V is along the field line, we will get 0 magnetic force. Angle of 0, sine theta is 0. And we'll get a maximum magnetic force when we are moving perpendicular to the field lines. A better way to think about this is the magnetic force acts only on the component of the velocity that is perpendicular to the field. So for this velocity over here, the one that I've circled, we can break that velocity into perpendicular and parallel components to the magnetic field, which I'll call V parallel and V perpendicular. The parallel component of the velocity is unaffected by the magnetic field. But the perpendicular component is going to experience that force. This perpendicular component is going to be V sine theta. So that's basically it. There's the magnitude of our magnetic force. We're going to skip forward a little bit. So to sum it all up, we only get a magnetic force on a charge if 1, the charge is moving, that is, it has a velocity that's non-zero, and it has to be moving, at least one component of it has to be moving across magnetic field lines. So we get a maximum force when we're moving perpendicular to the field, we get a minimum force, we get 0 force when we're moving parallel to the field or not moving at all. How do we determine the direction of the force? Well, we use our right-hand rules. The force is always going to be perpendicular to both the velocity and the magnetic field. So, what do we have? So here are 2 right-hand rules. If you've learned a different right-hand rule, just use that right-hand rule. Don't get confused. Either the top right-hand rule or the bottom right-hand rule. But basically, if we rotate around in the direction of the moving charge, if we point our thumb in the direction of the charge, the magnetic field points in the direction of our fingers, and the force is the direction out from our palm. That one's just fine. If you've learned one that's slightly different, that's also fine. Keep in mind that if we have a negative charge that's moving, that's going to reverse the direction of the force. A negative sign will flip that vector, we can think of. So we can just use our right-hand rule and flip the vector, or we could use a left-hand rule. So choose one and be consistent. Either always use right-hand rules for positive charges and left-hand rules for negative charges, or use your right-hand rule for all types of charges and just reverse it at the end if you have a negative charge that's moving. What else do we need to say about objects moving or charges moving through magnetic fields? Okay, so we know that the direction of our magnetic force is always going to be perpendicular to the velocity and the field. So let's imagine a magnetic field that points directly into the page, like so. And let's pretend it's a uniform magnetic field, even if I didn't draw it perfectly. If we're coming in, let's say we have an electron. So a negative charge coming in with some velocity v. Once it enters that magnetic field, has that initial velocity v, it's going to feel a force, and we can use in this case I'm going to use a left-hand rule to determine the direction of the force. So I point my fingers in the direction of velocity, curl into the magnetic field, and using my left-hand rule, the force is going to be straight down. So I will label my force in orange. Force is down. But since my force is perpendicular to the velocity, we're not going to get any work done. We won't speed up or slow down. All it's going to do is change the direction of our particle. And in fact, since the force is always going to be perpendicular to that velocity, we're never going to get a change in speed. We're only going to get a change in direction. Therefore, we'll get circular motion. Uniform circular motion, in fact, as long as there are no other forces acting. That force is going to point towards the center. And so, since we have uniform circular motion, we'll always get this circular arc of a particular radius. We can say that the magnetic force, the magnetic force is equal to the centripetal force, because it's the net force, or Q V B sine theta is equal to mv squared over r. We can use this to analyze the trajectory of our particle and potentially even find the radius if we know the mass, if we know the properties of the particle. So let's just go back. A little disorganized. Let's just go back and do one example. A proton is accelerated from rest across 20 volts of electric field. It then enters a perpendicular magnetic field of 25 microtesla. Find the radius of its trajectory in the magnetic field. And the mass of the proton is, of course, in your data booklet. So first of all, it's accelerated from rest across 20 volts. So we go from maybe 0 to 20 volts. There's some electric field here. And let's place our proton in that field. It's going to speed up to a certain speed, and then it will enter our magnetic field. Which I will draw in blue. It says our magnetic field is perpendicular, so I'm going to represent it as going into the page, but we don't necessarily know. Let's just draw it going into the page there. And the magnetic field is equal to 25 microtesla. Okay, we want to find the radius of trajectory of the magnetic field. We know it is going to form a circular arc, so we can just set the centripetal force equal to the magnetic force. But first we're going to need to find the speed, and we can find that speed using the electric force. We know that if we're accelerated across a voltage, voltage is work per unit charge. So work is equal to just charge times voltage. And since we start from rest, that work is just going to be our change in kinetic energy. It's going to be 1/2 mv squared. We can solve that for the speed of our proton as we leave that electric field. So V is going to be equal to, well, let me solve it, 2q voltage over mass, all under the square root. So plug that in. 2 times the charge on a proton, 1.6 times 10 to the minus 19 coulombs, times 20 volts, divided by the mass of a proton. Let me quickly look that up. Mass of proton is 1.67 times 10 to the minus 27 kilograms. So our velocity is going to then be going to be 6.19 times 10 to the 4 meters per second. That's the velocity upon entering our magnetic field. Then since we're entering a perpendicular magnetic field, we're going to get some circular motion with a force pointing towards the center. Let's just set up the equation. mv squared over r is equal to our magnetic force, which is just q v b, which should be lowercase because it's velocity, times sine of theta. But we're perpendicular to our magnetic field, so that sine of theta is just equal to 1. So if I want to solve for r, I just solve for r. I get r equals mv squared over q times v, which is just equal to m times v over q. So that is, oh, I forgot a b. That's what's going wrong. mv over qv. So again, the mass of the proton is 1.67 times 10 to the minus 27. The velocity is 6.19 times 10 to the 4 meters per second. The charge is 1.6 times 10 to the minus 19 coulombs. And the magnetic field is just 25 microteslas, 25 times 10 to the minus 6 Tesla. R then becomes, we plug it in, and we get a very large radius of 25.8, or to 2 sig figs, 26 meters. Quite large. We need a very large collider to measure that, or maybe it'll just be a small deflection that we're looking at. Anyway, that's basically it. Anytime we have that circular motion, we set our centrifugal force equal to our magnetic force. That's all. Bye. Oh, actually, that's not all. There's one last thing. Over the course of this course and over the course of this unit, there are a few particles that you really need to know off the top of your head. You don't need to memorize all their properties, but you need to know what they are, and you need to know how to find all their properties. Particles are the electron, proton, neutron, alpha particle, and photon. The electron, proton, and neutron are all the particles in an atom, and they should be pretty straightforward. Electron has a charge of negative E, proton has a charge of positive E, and neutron has a charge of 0. Their masses are all also given in the data booklet. But you also need to know what an alpha particle is. Alpha particle is a helium nucleus, which means it's made up of 2 protons and 2 neutrons. So it has a charge of +2. It has a mass of 4 atomic mass units. Yeah, so if you ever see an alpha particle or a helium nucleus in a problem, it's a charged particle with a charge of +2 and a mass of 4 atomic mass units. You also need to know that a photon is massless and chargeless, but I think that's all you need to know. That's all for real. Goodbye for real.